Welcome to the the Provost Graduate Student Lecture Series. My name is Jacques Verberschot. I'm the Graduate Program Director of Physics. Physics. And the reason I'm here is that I'm part of the selection committee for these lectures. So every year or twice a year, we get many proposals. We have a hard time selecting the best one. And my first criterion to select a proposal is whether I would like to attend the lecture. And I think this is a very interesting title. It's interesting for physicists. We actually have 3 physics students here. And we also have Yunlong's advisor, Piotr Jurek. And he can introduce Yunlong much better than I do. So I give the word to him.
Thank you. Good afternoon. My name is Petar Đurić, and I have been Yunlong's advisor since he has come here. I'd like to say a few words about Yunlong. He comes from China, from the beautiful city of Xi'an. Xi'an was one of the old capitals of China. Since his first days here, I noticed his abilities and skills. He took 2 of my graduate courses, and I was very happy when he asked me to be his advisor. I gladly accepted him, and since then we have developed a very nice relationship. In these few years that he had done research, he has been very productive. He already has published 5 journal papers, which is something that is not so usual in engineering. All these papers were published in most prestigious journals. Yunlong has also been invited to give talks outside Stony Brook. He gave a talk at University of Delaware to faculty and students. Of course, he has also given talks and presentations at conferences. His work has been on a very interesting theme. More recently, in the field of signal and information processing, we are interested in studying what happens in networks of agents when they do their own processing and they can communicate with similar agents in their neighborhood. So Yunlong has discovered some new results, new knowledge, and he'll present some of them to you today. Without further ado, Yunlong, the stage is yours.
Thank you, Professor. Hi, everyone. Thank you for coming here, and I'm very appreciated that I have this opportunity to have this to present our study and our research about the Bayesian models of social learning with random decision making. In the title, there are 3 keywords there: Bayesian models, social learning, and random decision making. So by this order in this presentation, I will explain them one by one and show the relationship between them. Okay. Now let's take a look at the outlines. In the first section, I will introduce some concepts and the problem formulation, and also give some explanation on the keywords. In the second section, I will introduce some Bayesian social learning theory. With the Bayesian models developed in the second section. In the third section, I will discuss a little bit about herd behavior. As you may know, the herding and the information cascade is complicated issues, and it is some hot topics in the study of social learning. So in this presentation, I cannot go into very details about herd behavior, but I will give some big picture explanations on herd behavior. In the fourth section, I will propose social learning in sequential decision-making system, which is an extension of the second section. And in the fourth section, I will introduce randomness in decision-making, which is I think it is novel in this area, and I will analyze how randomness can change the result in decision making. Okay. So, okay, now talking about the social learning. we must take a look at what is social network. A social network is a social structure made up of a set of social agents. For example, like us, we can be modeled as agents in the multi-agent system. And the social network, by its name, the network, there must be some edges between the agents. And the edges are the dynamic relationship between them. Modeling of agents, interactions, and the learning has been studied in wide literature. That's a social network. Okay, so what is social learning? Learning by individuals from the behavior of others is common in social network. When people are making decisions with available information, it is natural that they refer to the previous decision, refer to the decisions that has been made in similar situations. And this is a learning process. Technically, learning involves 3 steps. One is obtaining observation, which can be others' decision and also private signals. The second step is extracting information from the observations. Third step is making decisions based on the information extracted. That's the 3 steps. The observations include 2 parts. One is a private signal. The other is the decision of others. So in social learning, the agents not only learn from the private signal, but also the decision of others. They must make inference about the information contained in others' decision. Modeling the learning process by Bayesian methodology is of primary interest in the study of Bayesian social learning theory. Also, it is a primary interest of this talk. Let me show you some examples. Here are some examples about social learning. Social learning can be based on various types of information. For example, when we see the comments on movie, companies, restaurants, on internet, like Yap or YouTube, for example, things like that, we get information from the comments. And based on the comments, we make our decision. When we shop on Amazon, based on the remarks and the stars, we make decision whether to buy this item or not. Same thing, investment in stock market, sorry. Also, even today's lecture, I'm spreading information. So maybe I would like to say you can learn from the lecture, or get information from this lecture. You extract information from my lecture, and the decision here. Okay, let's talk about like this. You make decision to, the decision of your is to be here or not to be here, to join this lecture or not. The information you get is my advertisement, the title, the abstract, and also before you come here, you have discussion with your friends. You know others' decision, sort of. So based on others' decision and your private signal, you decide to whether to join today's lecture. And that's one kind of social learning. Okay. As I have already pointed, the information extraction is very important in social learning. There is an important category in this study is the Bayesian learning method. Can we extract the information by Bayesian methodology? Yes, sometimes it can be. In the Bayesian social learning theory, a social agent forms its belief as a posterior probability distribution conditioned on all information available to it. In plain word, it's a posterior probability given by this. So it's a conditional probability of the state of nature conditioned on available information. Thank you, Professor. Thank you. Yeah. Here, let's consider the restaurant example. People making decision whether to go to the restaurant or not. Then the state of nature is whether this restaurant is good or bad. That's the state of nature for the restaurant. And available information can be comments and the private signal, like how many stars it has in Yap. Then, the information extraction is modeled by the following update of belief through the Bayes rule. The belief is updated from a conditional probability. It's out of battery, so I have to use my finger. Sorry. So the update is from condition on private signal only to condition on private signal and the decision of others. This process can be done by Bayesian theory. And this equation is the essence of the Bayes methodology to update the belief through Bayes rule. In this process, the information has been utilized. Okay. After forming the belief, agent can, this is the third step of the agent. After forming the belief, an agent can make its decision by maximizing some utility function. For example, a selfish agent aims at maximizing the personal reward. In game theory, the agents are assumed to be maximizing the personal reward, things like that. And by contrast, in the study of sociology, I know someone assumed that the benevolent agent maximizes the utility function, which considers both the personal reward and the social welfare. Normally, the decisions here, my remark on these two models, the selfish agent and the benevolent agents, the decisions are deterministic. In other words, once the belief has been formed, the decision is made according to a deterministic mapping from belief to action. Let me use an example to explain this. Suppose one agent has some available information. Then, once this available information is given, in these two models, its decision, and once the utility function is deterministic, then its decision is deterministic. For example, as I will show later in the examples, okay, let's don't consider it too much here. I will show you in the fourth section of this presentation. Okay. However, in some scenarios, the behavior of agents may be random naturally. For example, there is a chance that an agent refuses to behave as predicted because of some random disturbance as mood misleading information. It's like sometimes I refuse to buy the best seller. I'm inclined to buy the best seller of Amazon, but it's not definitely. It's not deterministic. If I'm not in good mood today, maybe I will refuse the best seller. But there is still a very big chance that I will buy the best seller. Then my decision shall be random. There is randomness in my decision making. And in the third model of this presentation, I will show a possible model to introduce randomness in decision making, and we will revisit this topic later. Okay. In the second section, I will introduce a little bit about Bayesian theory. Let's use, this is the simplest model I can find. This is a binary model. Okay? An agent gets a private signal which can be either 0 or 1 according to the following binary model. The private signal can be generated by either a good state or a bad state. We can imagine the state of nature. Let's consider again the restaurant example. In the restaurant can be a good restaurant or a bad restaurant. If it is good, then theta equal to 1. If it is 0, then it is 0. The private signal here is say it's a looking of this restaurant or the menu, and the private signal is compressed, is highly compressed to 1 bit. The private signal here is just 0 or 1. Here, 0.9 means that if it is a good restaurant and you get a good signal, the probability is 0.9. Then, if it is a good restaurant, you get a bad signal, it's 0.1. Similarly, if it is a bad restaurant, the distribution of signal is in the second line. Okay? That's a binary model, binary observation model, I think. Okay. Before getting S, the agent has no information about the state of nature. Then its prior is denoted by uniform distribution, which is it's half-half. Half chance to be a good restaurant, half chance to be a bad restaurant. Then with the signal, with the private signal S, the agent's belief pi is updated through Bayes' rule by this equation. May I ask, are you guys, can I assume that you, I promise this is the only equation in this presentation. I have already deleted all the equations. So
spend some time on it.
yeah, but so by plugging in the numbers, the prior is 0.5, 0.5, 0.5, and the likelihood is a distribution on the table, in the table. It's 0.9, 0.2. Anyway, if you are not familiar with Bayesian theory, you know after the update, the posterior distribution has changed from 0.5 to 9/11 if it gets a good signal. By contrast, if it gets a bad signal, the belief decreased from 0.5 to 1/9.
So can you explain the equation?
Yeah. The equation here is okay. Okay, this term, S condition on theta equal to 1, is that it gets a signal S if the restaurant is a good restaurant. And the S condition on theta equal to 0 is that get this S condition on this is a bad restaurant. And the prior here is 0.5 because we assume an informative prior. Okay.
Don't press it all the time, just.
Yeah, okay. Thank you. Okay. Okay, next. That's the information extraction part. Next, we will go to the decision-making part. After forming the belief on the state of nature, the agent must make a binary decision, either 0 or 1, according to the belief. The reward of the agent is said to be 1 if the decision is correct and 0 otherwise. Aiming at, okay, if it is a good restaurant and the agent decides to go to the restaurant, then the reward is 1. If it is a bad restaurant and the agent decides to go into the restaurant, then the reward is 0. Aiming at maximizing the expected reward, the agent shall make its decision as 1 if its belief is greater than 0.5 and 0 otherwise. If I have a strong in the deterministic decision making, if the agent has a strong belief in the restaurant, then it go. Otherwise, it doesn't go. Here we have some remarks about how agents learn from the private signal. The model shows how a single agent learns from its private observation by utilizing the information contained in it. It can be shown that the agent's expected reward is strictly greater than the expected reward of an agent without using the private observation. I think this is the essence of the Bayesian learning. The Bayesian learning guarantees that you get something. As long as there is information contained in the private observation, then you get something. Here, you get that the expected reward is strictly higher than the expected reward without using the private observation. Okay. Next is how we learn from the neighbors. Because as I pointed out in the first section, sometimes information comes from two parts. One is private information. The other is information from neighbors. How we learn from neighbors. Now we consider a system of two agents, which are denoted by A1 and A2. The first agent, A1, behaves exactly in the same way as the process we have just described, learn by himself only. Then how does the second agent, A2, learn from the decision of the first agent? In Bayesian models, A2 use Bayes' rule again. The second agent belief, pi2, is then defined to be the posterior probability conditioned on not only S2, but also alpha 1, which is a decision of agent A1. The calculation of getting this pi2, I will not show the details about how to get this pi2, but the idea here is the learning of agent 2 is from theta equal to 1 conditioned on S2 only to conditioned on both S2 and alpha 1. That's the update. Even without showing the calculation details, we can make some claims about this. If agent A1 makes the decision as 1, the belief of A2 on good state will be strengthened. Mathematically, the posterior, the updated posterior, is greater than the posterior conditioned on private signal only. Vice versa. We have that if the agent A1 makes decision as 0, then it will decrease the belief of the second agent. Here, the update of this can also be regarded as if it has been updated twice by two parts of information, S2 and alpha 1. Learn from S2 and learn from alpha 1. Let me use an intuitive example to show this. When someone makes a right turn in the crossing, if some places it is no turn on right, some places it is you can turn right on right. If I observe some car turn right under right light, this will greatly encourage me to make the same decision. That's how the first agent's decision affects the second agent's decision. Because I learn from his behavior. And I assume he has some knowledge and information. Yeah. Yes.
So what's the formula for T for the I think you can always define such a formula as when alpha is 1, if it's greater than the second, right?
Okay, that's a very good question. Here, I write this equation because I assume now we are still in a binary model. I'm not saying it is always true. I'm saying by this binary model, we can have this simple equation. If it becomes more complicated, then
Previously we defined the theta pi or the belief.
Yeah.
It's a function of theta and the S2, right?
Yeah.
And now you're defining the pi 2, which is a function of theta alpha 1 and the S2.
Okay.
The same dependent variable. Do you have the same definition of the pi?
Okay. My answer is that the theta conditioned on S2 only is how they learn from itself, how it learns it by itself. Right. Well, if it is conditioned on S2 and alpha 1, that's how it learns from not only himself, but also the previous decision. That's learning from neighbors. This is the result of learning from neighbors. This is the result of learning by itself. Yeah, thanks for asking. Yeah, and okay. Yeah.
The signal is the same for both. They observe the same signal or they observe different signals?
Okay, in this example, they observe same observation models, yeah. Okay. With a Bayesian model in previous section, we can have some discussion about the herding. The results on the previous slide help us understanding the following. One is inclined more to go to the restaurant with more customers to purchase items with better selling history. That's why, because the help of the previous decisions, because of the decision of others, we extract the information from others' decisions, which make us inclined to buy the best seller. One important reason for this preference is that the utilization of the information conveyed by others' decisions. However, sometimes this utilization of information does not necessarily give good result. Why? Let me show you the example here. In stock market, the information sometimes can be interpreted in incorrect way. See, the investors are making decision about sell or buy. And at the beginning, it is something, I cannot say it clearly, but this guy is telling Excel, and then it becomes sell, 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 sell. And suddenly, there is one guy say goodbye, then it becomes buy, 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 buy. That's one example of herd behavior. Even more. That's literally herd. In herd, I think it's sheep or the goat just blindly follow the previous goat, and no matter what is waiting for them. Okay. Let's discuss it a little bit about the herd behavior. Why we have herd behavior? Now we consider a scenario where 10 agents have made decisions before A11. When it's A11's turn to make its decision, it is so strongly affected by the previous decisions. By this equation, we say that here, this sign means that it is much greater than independent work. This is the independent work, learn from private signal only. This is learn from previous decision and the private signal. This is much, much greater than independent work. Then agent 11 is strongly affected by the decision of others. As a result, in some extreme cases, this probability quantifies the effect of how the previous decisions affect the A11. This effect becomes so large that no matter what private signal is, the belief of A11 must be greater than 0.5. In such cases, A11 makes decision as 1 regardless of private signal by using the deterministic decision-making policy, if it is selfish. Then A11's decision contains no information about its private signal, because its decision is independent of the private signal. Then there is no information contained in his decision about the private signal. Sometimes one works, okay, here is another example. Sometimes one works through the red light when no car is coming. We can see it especially in Manhattan City and in the crossing. Normally, it happens when lots of pedestrians are doing this together. If I say the people around me making this decision to jump the right traffic light, then most likely I will do the same thing. Even my private signal is red, and my wisdom tells me don't do this. But that's how how it hurts. Okay, that's some discussion about Hertz. Next, I will show the social learning in a specific sequential decision-making system, and this is an extension of the section 2. Excuse me, may I know the time? How many? Okay. Let's take a look at this cartoon. This is the sequential decision making in the studied system. At the beginning, the first agent makes a decision based on private signal only. Then the second agent makes a decision on the first decision and the second private signal. Now it comes to the third agent. The third agent makes a decision based on two previous action and the third signal. And it works like this in this figure. N agents make decisions one at a time in a predefined order. Every agent's decision can be observed by the following agents. The agents form their beliefs on state of nature by using Bayes' rule. That's why we say it's Bayes social learning. In this diagram, we describe it more mathematically. The private signals are denoted by Y1, Y2, Y3. And the decisions are alpha 1, alpha 2, alpha 3. When agent A1 makes a decision, it broadcasts its decision to all the following agents. Same thing for A2 and A3. I will say I will not go very details about how the Bayesian learning is implemented in this sequential system, but I will make some claims, some interesting results here. In this system, the earlier decisions contains more information because they rely more on private signals. When it comes to the 10th agent, its decision has been affected by 9 previous decisions. Well, the first agent's decision is based on his private information only. Compared with the later ones, the earlier decision have larger effect on the evolution of belief because it contains more information. Consider the comments on YouTube. If all the first 10 comments are negative, there will be less chance to get a positive one in the following comments. That's how the public opinion been formulated. I think we have the experience in real life like this. The decision of the first several guy, Okay. Another example here is, suppose that in a country, the government pays $50 for each comment that guides the public opinion to a correct decision. Then that's how the comments affect the others' comments. If a news has been published and many people say, wow, it's good news, wow, the government is good, so good, then you can imagine how the following comments will be. This will be effect, yeah.
What do you mean $50?
You know what I mean. I will explain it to you after this. Okay. With this binary observation model, it can be shown that herding starts in finite time with probability 1. Okay. That means the herding will definitely happen in this studied model, in the binary model. Okay. Now, we propose a random decision-making model here, where the agent makes decision according to this. Right now, okay, consider a case when the private signal, or when the belief, consider a case when belief is 0.8. By deterministic policy, this guy will make decision as 1, deterministically. However, now we let him to flip a coin, unfair coin, with probability 0.8 to be a head. And if it is a head, then it makes decision 1. If it is not head, it makes decision as 0. That's why I say it's random. Even the belief is here, the the decision is not deterministic. It's not deterministic mapping from belief to space, to action. Mathematically, it can be modeled by a Bernoulli random variable parameterized by AN's private belief, a pi n. I'm sorry, this is not beta n, it's pi n here. It's pi n. Okay, that's a proposed random decision making. Here are the results of this random decision making. The randomness introduced less correlation in decision making because now you rely more on your private signal. I cannot, unfortunately, I cannot here using intuitive examples to explain this, but this can be shown by mathematics. Okay. The second result here is that the randomness in decision making allows the agent to be an outlier. This is true. Even when the private signal, private belief is 0.99999, there is still a chance that it can be an outlier. And if outlier shows in the system, then Hertz could be break. That's why we say herding can be prevented in the studied social system with the random decision making. Of course, when we claim this, we must first define what is herd in this study. By our definition, the herd defined by us is it's a very strict condition, but we say such strict condition can be avoided. Well, of course, everything, like every coin has two sides. The expense of preventing the preventing herding is that the randomness decreases the learning speed of the sequential system. And that's an expense here. Okay, that's a final section here. Let me summarize what I have just discussed. We presented a series of Bayesian models from the study of social learning system, learning from private signal, learning from neighbors, and then learning in the sequential system, and learning with randomness. The Bayesian models reflected the update of the belief through information extraction. That's why some people like Bayesian models in study the social learning, because the Bayes rule, in my opinion, in some aspects, the Bayes rule naturally imitates how human beings learn from things. We update the belief, maybe not by Bayes rule, but we update belief. The utilization of information from others' decision may result in herd behavior. And finally, the randomness in decision making can prevent herd behavior. That's my concluding remarks here. And it's done now. It's a Q&A.
Okay, thank you.
Thank you. Thank you. Thank you.